afternoon to most of you, and good morning to the colleagues in the US. So I actually gave a similar talk earlier, actually to several conferences and universities. So if you have heard about this before, so I apologize. But let me start. This is really a summary of your work in the past 5 years in our efforts to develop a better inherent string method to model the metal additive manufacturing process, and in particular, the laser powder bed fusion process. So I'll talk about the background, the model, and some of the applications. So we got the EOS M290 machine about 6 years ago now. And the first thing we did, of course, just like everyone else, is like printing some, tensile bars and try to test them. And lo and behold, we learned a lesson right away that it's not that easy, right? So you insert the support structure, and then you see a lot of cracking going on, and especially when we were processing titanium, Ti64 or Inconel. And this problem is it's very prominent in these two materials. So at that time, we were thinking, okay, maybe it's very good to try to apply topology optimization to try to design support structure to help release the residual stress in the support to prevent this kind of build failure. Because anytime you get cracking, it may cause build failure, and if it's not causing build failure, there may be substantial amount of distortion, after you print the parts. So the problem with topology optimization is that it needs a lot of iterations. So basically, do it the four problems to try to predict residual stress or distortion, and that's computationally pretty intractable at that time. So we really wanted to develop a method to accelerate the prediction of part scale residual stress and distortion. So we were looking in the literature at that time, and kind of get interested in the inherent string method, and which was really developed by Professor Ueda in Japan, early 80s. Late 70s timeframe. And the whole idea of this method is to try to, model the deformation introduced by welding. At that time, there was no additive manufacturing like today. And, it was just modeling, simple welding problem. And the whole idea there is to, try to capture the deformation introduced by welding by an inherent string. So it's really an effective eigenstring representing the deformation. So the whole problem can be simplified into a quasi-static structural analysis problem. So no more heat transfer simulation is needed in this model. And what that is to represent the inherent string by the plastic string introduced by the welding process. And so that can be done, numerically, if you know how much plastic string is being introduced by the welding process, or experimentally, you can measure, do experiment, and then try to, back calculate what the plastic string is being introduced by the welding process. And then we were trying to apply this method to predict the DED process, right? The laser-based process by simulating the laser DED by depositing different number of layers, and then so this is of course doing detailed process simulation by following the laser heat source. The moving point heat source that's simulated by the GODAC model. And then from this process simulation, we extract the plastic string and then putting back into a quasi-static analysis, through the original inherent string method to try to, predict the distortion. And so comparing the detailed process simulation using this moving point source model and comparing that to the original inherent string method that's defined by the plastic string only, then we get pretty large errors when we compare the tip displacement, anywhere from 28% almost to like 50% in the displacement, tip displacement of this cantilever structure. And independently, we find a paper in 2017, so work done by Dr. Bugatti from Italy, and he also did this first similar thing, but applying to the laser power back fusion process, and find that the original inherent string definition, applying the inherent string model to model the laser power back fusion process, you get a substantial amount of error, for different cases. So anyways, we were proposing a new model such that we can extract the inherent strings from a detailed process simulation directly, so that we don't have to do a extensive inverse problem to get the inherent strings. So this is the new definition that we're proposing. So not only we include a plastic term, but also two elastic terms, and we separate these, the time that we are acquiring these string terms from the detailed process simulation, okay, into what we call the intermediate state and steady state. So let me show you a plot that will make it more obvious what I mean by intermediate state and steady state. So this is a plot, during the deposition of a three-layer scan of a single wall. And so you see the evolution of the elastic string, you see the evolution of the plastic string, for each layer, okay? So our idea was to try to capture, really, you have a molten liquid that's cooling into a solid, okay? So that thermal string has to somehow transform into mechanical string, but how? So that's what we're trying to capture here, okay? So a lot of the thermal energy, it's actually transferred into mechanical energy by compression. So this is the largest at this stage, when there's like a rapid expansion of the metal pushing the material into plastic deformation. So that's what we think part of the thermal energy is getting transferred into mechanical string at the intermediate state, where the compressive string is the largest. Okay, so that's the first two terms of this new model that we propose. So including the plastic and the elastic string. Okay, and then after the build is finished, we get into a steady state. So everything cools down, but so at the intermediate state, actually the material is still quite hot. It's not at the melting temperature, but it's still very hot, okay? At maybe still at like a couple hundred, degrees Celsius for typical materials like Inconel. Maybe 800 or 900 degrees Celsius, even after, this intermediate state occurs, okay? Still very hot. So that thermal energy has to go somewhere, right? We need to capture that. So what we find out is that, this is a good term to include, okay? What the elastic string at the steady state after everything is cooled down. So that's the term that we use to capture, how the rest of the thermal energy get converted into mechanical energy. Okay, so that's why we're including the elastic term at the steady state. So from this model, we can extract the inherent string from a detailed process simulation based on the moving point source model. Okay, and we were just modeling a multi-layer deposition based on the DED process. So this is the inherent string, and you can see that along the scanning direction, it has the largest compressive string, as you would expect. And the MEL pool, of course, is elongated, so you get a larger magnitude along that direction. Transfers to it, you still get a little bit of compressive string. And then in the build direction, which is represented by the black curve, because of the Poisson effect, you get extension in the build direction. So that's what we're seeing here in the inherent string in the build direction. So based on that, we extract these inherent string and then we applying that to the model but only doing the quasi-static analysis. And the errors become a lot less, going from 28% to almost 50% down to less than 11%, if you would, for different number of layers of deposition. So so we got a lot better results, and for a much faster simulation, much more efficient simulation time. But I think you may wonder if I am doing a process simulation in detail already, then why do we need to do inherent string model? Well, so for laser powder bed fusion, that's very difficult to do moving point heat source model for the entire part. That's consisting of millions and billions of scan lines. So so the idea here is that to use a multi-scale approach. At the fine scale, we define a process simulation model that we're doing in detail with moving point heat source. So solving the thermomechanical coupling problem. And then, so from that, we can extract the inherent strings. So we take the steady state inherent strings and then applying it to the entire model, okay, at the path scale. So at the path scale, we are only applying the inherent string over the entire part, and then just doing a layer by layer static analysis. Yeah, so so this is a just a representative process model for the EOS process. So the EOS process, typically you have a air scanning pattern at one layer, and then the next layer you rotate by 67 degrees. So that's to try to capture a rotation pattern. And from that, we can extract the inherent string curve, and then we just take an average of the middle part of the curve as the inherent string vector, which we would then apply to the path scale analysis. Okay, so we apply that to this is become a very benchmark problem in the additive manufacturing community. So we will apply to this part, cut off both sides, and then you see the one side is actually higher after cutting off, because like some of the stress already get released from the other side, so you get a non-symmetric displacement on the cantilever structure. But by and large, we were able to capture using the modified inherent string method. But we were able to capture distortion quite well. And then we compare, for different lengths of this double cantilever structures, how does the comparison between the modified inherent string method and the experiment. So we measure the displacement here, and yeah, so all the errors are less than 10%. This one. Okay, so one thing that we were focusing on was really on distortion in the first couple of years that we were looking at this problem, and then we realized this overestimation of the stress using the modified inherent string method. So we were always wondering why the stress on the surface is so much higher, but then internally within the structure, it looks reasonable. Okay, so later we find out that maybe that something has to do with how we apply the inherent strength to our layer-wise static finite element model. Okay, so in the previous results, we were using material properties at ambient temperature. So in the inherent strength model, all the properties, okay, is not temperature dependent, right? Because we don't have the heat transfer anymore. So all the properties we are using is at the room temperature in the inherent strength model. So now we realize that, because of the way that we are extracting the inherent strengths, like we divide that into intermediate state, which is very hot, and the steady state, which is at the room temperature. We are to do this implementation in 2 steps. The first step is during the deposition, we should be applying the material properties at the intermediate state at temperature, okay, which is a lot higher than room temperature. And then after that, subsequently, when it becomes part of the structure, then we switch that into the room temperature properties, for example. So this becomes a 2 temperature model instead of a using single temperature properties. So the stress becomes a lot better in this case. And as you can see, previously there was actually a 20% difference in the formation stress if we only apply properties at 1 temperature. And now if we apply the properties at 2 different temperatures, then the result becomes a lot better when we talk about the formation stress distribution. But we need to look back at the displacement, how that goes. So because now we are encouraging local plastic deformation, then the overall displacement become smaller. So that's how it goes. Okay, from the previous procedure, we were getting an overestimation of 2.8%, and now we're getting an underestimation of 3.6%. So it went the other way. But but that is still acceptable. But the good thing is that we capture the stress a lot more accurately now using this 2 temperature model. And then we also did a XRD experiment on the canonical part that we have built. So we take it to a local company to do an X-ray diffraction experiment to measure the residual stresses on top, and then we compare that the old procedure for implementing the inherent strength method compared to the new procedure. And you see that the result compared to experiment is a lot better. So we built 2 of these models. That's why you see experiment 1 and experiment 2. So we built 2 different parts. They're exactly the same, but they are just on different locations on the build plate. But you can also see there's some variation in the measured stresses between the 2 samples, even though they are exactly the same. So just to show you, there is definitely variation in the process, location dependency there. But you can see that the new implementation of the modified inherent strength model is a lot better, has a lot better prediction than the old model. We also measured distortion on the center line on the side of these 2 printed canonical parts. So I apologize, I wasn't showing the 3D model in the previous slide, but now you can see what I'm talking about for this canonical part. And the interesting thing about this canonical part is that initially it has thin wall going up, and then as it is going up, it becomes an overhang that is also changing in in the wall thickness. So as it's converging, there's, obviously there's like lots of distortion, when at the point when it converge. So this is a good part, that, many people use to compare to their part scale distortion model. And so the experiment, basically the gray area is the standard deviation. The black dashed line is the average from the two experiments on the 4 center lines that we are measuring the distortion on each of the parts. So so that's an average over 8 center lines for the 2 parts that we have printed. Actually, we compare that, and our displacement now is actually a little bit underestimated. For the reason that I mentioned, because when we implement the 2 temperature model, then usually the displacement get a little bit underestimated, but we improve the stress estimation substantially. So that's the expense that we pay, but maybe we're still trying to look into how this distortion underestimation can be improved in the future. So just to I'm running out of time. Just want to present several applications, because I talk about the motivation for developing this enhancing method was to try to do topology optimization and try to prevent build failure, build cracking due to residual stress. So we apply this method to try to estimate, enhancing method to try to even calculate the J integral, so that we can compare the critical J integral to the actual J integral for a part, so that we can predict cracking in the part. I don't have time to go into all the details, but this method actually worked out very well. We combine enhancing method, global local analysis, and we homogenize ladder structures. So we combine a lot of different techniques to make this work in an efficient way. And so we were able to predict cracking at the corners of these parts, and then we were able to, based on the result, we were able to change the design. First design we made was to make the corners to be a solid support instead of a block style ladder structure support. To strengthen the corners so that you don't crack. They don't crack anymore. Another design was we make, instead of a sharp 90-degree corner, we put in a fillet and smoothing the corner to reduce the stress concentration. So after we printed this out, we see no cracking anymore. But at the corner that we have cracking, that's still cracking. So we didn't do anything on that. Okay, so we were able to also, integrate the inherent string model into topology optimization to prevent build failure. So just say an example here with unoptimized support. We see cracking in the support. This was printed in Ti64. And then we use a gradient lattice optimization technique and put in the inherent string method to predict the residual stress. And we were able to come up with a optimized support that does not crack anymore. Also apply that to build orientation optimization. So we use a particle swarm method and just applying the inherent string model to predict the stress. So finally we were able to identify the optimal orientation that has the least amount of maximum residual stress. Okay, so this is a totally new application, trying to design a scanning path to reduce this residual stress. Okay, so this may be very important in printing brittle materials, and we were able to optimize the scanning path on a island scanning pattern strategy, and was able to reduce the distortion after cutting by 40%. So we think that this technique may be very useful in printing brittle materials in the future. Okay, so I'm not going to go through my conclusion, but I rather like to answer any questions that you may have. So thank you for the opportunity, to give me an opportunity to present here, and I appreciate your attention, and any questions are welcome.
Thanks a lot, Albert. Very interesting presentation. So we have a couple of questions. Mark.
Yes, thank you very much. Thank you, Albert, for the nice talk. I'm still a little bit puzzled with this inherent strain concept. And the reason why I'm puzzled is that I understand that it can help you in studying the distortions. But if you're looking at the residual stress, that is mainly driven by the elastic strain only. And the crack and the risk for crack propagation will strongly depend on the residual stress state. So on the one hand, I see the importance of the elastic strain, which drives the residual stress, and then your inherent strain concept. But I'm a little bit puzzled how you managed to use that concept for both the purpose of looking at distortions and actually cracking, which is driven by the stress state.
Yeah, so I mean, I think we did enough like validation, like from experiment to show that the stress we're getting from this model that we're proposing is correct. So and I mean, if that's the case, then I mean, I don't see why we cannot apply that to predict cracking, because if what we are calculating is accurate, then I mean,
my question is more fundamental. I would say that the residual stresses, they depend on the elastic strains and only on the elastic strains. So your inherent strain is more rich. It contains information from the plastic strain and the elastic strain. So how can you use the one for the other? This is what puzzles me.
Right, but then but in the actual material, you are actually causing plastic deformation. So on that you may be able to formulate a model just based on elastic strain, but in the actual material physics, you are actually seeing a lot of dislocation density happening, very high dislocation density, in fact. And I'm sorry, I respectfully argue with you that I think that the welding process is causing a lot of plasticity. So that's why we think that this model is more accurate than doing the elastic strain.
I think I have to look deeper into it to
Why?
Thank you.
Yeah, thanks.
Thanks, Mark. Daniel, you have a question?
Yes. Could you please comment? I understood the concept of your intermediate stress connected with the intermediate in-process temperature, which is kind of cooling down as related to melting, but not cooling down to the plate temperature completely. And if you're doing, I understood how you do it. If you do the micro simulation with following the laser path and so on, so this is clear. Could you comment how you come to a intermediate temperature for whole build simulations, or for the layer by layer stuff, because you didn't comment how you actually get to this temperature information?
Okay, yeah, sure. So yeah, that's a good question, and we usually consider the intermediate temperature as when the laser heat source just go past the point of interest where we are calculating the inherent strain. So why pass through it? Okay, not until the entire part is done, but immediately after it passes through the material of interest, and that's where the largest compressive strain occurs. So that's where we are collecting that information in the representative process model.
Yes, I've got that, but
Okay.
now you want to simulate a part, let's say 50 times 50 times 50 millimeters or something like that.
Okay.
And you're not and you're not following the laser path, but you have
No.
to do some homogenized approach. And
Yeah.
for this, you need to calculate to assume or to get by some way to an intermediate temperature for which is going to be different at different locations of the component.
Okay.
And
yeah.
how do you do
okay.
that?
I see. Okay, got you. Yep. So we just estimate that from the representative model. So all the intermediate temperature will be the same, and for the entire part. And I understand your concern about in reality it may be different, but for me, for us, there's so much we can compute. We cannot wait just from the practical point of view, right? I mean, that's the whole purpose of developing this method, is to balance between the accuracy and the efficiency. And so from I mean, we can try to do like maybe a little bit more accurate, is to try to do a layer wise heat transfer model to estimate that, but that will be again computational time. Okay. So that's why we try to balance accuracy and efficiency. That's why we just taking the intermediate temperature from our process model.
Thank you very much.
Yeah, thanks.